for the difference, let's talk Venn diagram for a moment. Okay, if we look at the Venn diagram, and here's A and here's B. What things have we talked about as far as A and B so far? What things have we talked about? In these regions, what have we hit so far? Well, one is the intersection. So the intersection is which color? Or which part of this is the intersection? Sliver overlap, right? Another thing we've talked about is the union. And what would the union be? All the circles with the overlap, right? So we've talked about that. Have we talked about this part out here yet? What would that be? That's right. That's the complement of A union B, right? So we've talked about that. So use your creativity here. What haven't we talked about yet? I like it. Oh, I love that. That's so great. But we really haven't talked about this part or this part or the combination of those two. Those are the only two. Mathematicians love to put names to things. And so either blue or green is what we're going to call the difference or the relative complement. It's a complement, like this A is a complement of B, but not the universe. And this other moon would be the complement of A, not the universe. So the way that we would describe these is the relative complement. It's X is an element of A, but it's not in B. Does that make sense? So it's going to be this is going to be the part that's not, it's A without what? Intersection. Just a descriptive term, relative complement. But what's kind of nice about it is some nice symbols we can use in proofs. But just whenever you see A/B, it's the intersection of A and not B. It's element of A and not B. Okay. Are these equal? Is A intersect not B the same as B intersect not A? Okay. In my drawing here, which one is A intersect not B? Yellow or blue? Yeah, it's A without the intersection or intersecting the complement of B. And then for B, that's the blue, not the complement of A, or intersecting the complement of A, not the intersection. I think this is the clearest way, don't you, to describe it without the intersection? I think that's the clearest way. But they're not commutative. Notice that. Okay, and so you can look at these. Let's just do a couple of quick examples here. We're going to look at A not B and B not A. A not B is going to be any intersections between A and B? No, so it's just going to be 1, 2, 3. It's just A itself. B not A is just going to be B itself, 4, 5. But is there an intersection between these two? A, B, C and B, C, D, E, F. Where's the intersection? B and D, right? So what we would say for A not B, it would be the A and C for A not intersect part with B, and then B is going to be the EF. And then, of course, we can have, if you do, this one's really good, you're going to have intersections here of 2 and 4. And so if we look at A intersect the complement of B, or A minus the intersection is just going to be 1, 3, 5. What's B minus the intersection? Nothing, because that would be inside. If you're looking at that one, B would be inside A. And so if you were looking at not the intersection, it would be not itself. So it would be the empty set. All the symmetric difference is both differences, union of both differences. So think of it as the yellow and the blue together. And so when you see this triangle, they're looking at the symmetric difference, just both of them, A difference B and B difference A. It is commutative. These will be commutative, and they'll also be associative. So that's kind of cool. All right, so the symmetric of A, look for the intersections first, like this A, B, C, D. Here's the intersections, B and D. And so the difference of these would be A, C, E, F. What are we leaving out? What are we leaving out here? Asymmetric with B, you're going to have asymmetric B. What isn't included if it's A, B, C, D, and D, B, D, E, F? What isn't in A, C, E, F? No intersection. Leave out intersections. So if you look at this first one, 1, 2, 3, and 4, 5, are there any intersections? So the symmetric difference is just going to be all of those, 1, 2, 3, 4, 5. If you look at the intersection here, the symmetric difference will just be 1, 3, and 5. All right, so I'm going to turn you loose on these. See what you can do with 1 ABCD, 2 ABCD, and the Venn diagrams, A, B, and C. There's several parts there. And 4, lots of Venn diagrams. The proofs we'll get to at the end of the hour. There's just 2 of them and a challenger. So go ahead and work on those.